Welcome, I'm Nan Jokerst, and in this video we will talk about vacuum systems and mechanical pumps. Vacuum systems are used to deposit thin layers of materials such as metals and insulators onto our samples. The thicknesses of these vacuum deposited layers are very thin, on the order of 5 nanometers to 250 nanometers, and are used in many materials and devices, including integrated circuits and the lasers and metamaterials that my students make in our clean room at Duke, as shown here. For high yield, we need very pure layers of the thin film materials that we deposit. This first requires an extremely clean environment, which can be found in a high vacuum system. Second, we need to use high purity source materials for deposition. These two conditions help us to minimize the number of impurity molecules in our thin films that are introduced during the deposition. These impurities can even be air molecules, so a clear path without air for the deposited material to travel from the source to the sample during deposition, as shown in this animation, is very important. A vacuum chamber is designed for high-yield, thin film deposition, where more than 99.9999% of the air is removed. Another way to think of just how empty a vacuum chamber is: for every 100 million air molecules present in the chamber when open to room air, we remove all but one. How do we do this? Through the use of vacuum pumps that remove the air from a sealed vacuum chamber. Let's take a look at a vacuum chamber at Duke. Hey, Callie. Hey, I understand that you're making some photodetectors in the clean room today. Now, a photodetector is a device that's an electrical device used to detect light and output an electrical current. Callie, can you take us in and show us the vacuum system that you're using to deposit the contacts onto your photodetector?
Sure, I'd be happy to. Let's gown up and go into the clean room to see the system.
That sounds great, thanks.
This is a metal deposition system, and we can see the place inside where the vacuum pumps will remove the air from the chamber. This orange rubber ring is a vacuum gasket that seals the chamber from the outside air when we close it. Let's close it now, and we are ready to pump the chamber down to vacuum.
The most common type of vacuum pump is the mechanical pump. There are many different types of mechanical pumps, but all pumps serve one basic purpose: to push air out of the vacuum chamber. This is an important point. Mechanical pumps do not suck out air. Instead, they push volumes of air out of the chamber. By pushing air out of the vacuum chamber, there's less air in the chamber near where the pump is pushing out the air. One type of mechanical pump is the rotary vane pump, shown in this animation. The rotor of the pump pushes a small volume of air to an outlet pipe with every rotation. But a typical pump rotates at over 1,000 RPM, so with every rotation, air is pushed out, leaving less air in the chamber near the pump, creating a low pressure region in the chamber. This low pressure region in the chamber near the pump causes the air in the rest of the chamber to move toward the low pressure region. This movement of air is called diffusion. The same process is at work when I wear perfume. I spray the perfume on, and the molecules of perfume diffuse throughout the room, and everyone can smell my perfume, especially if I wear too much. The same process is at work in vacuum systems. The pump pushes air out of the vacuum chamber, and the remaining air in the chamber will diffuse toward that low pressure region. As we remove the air from the system, the chamber pressure drops, and the difference between the low pressure and the higher pressure areas becomes smaller. When this happens, the pump is less and less effective at pushing out the air. After the pressure reaches a few torr, which is called a rough vacuum, a mechanical pump is increasingly less effective at reducing the pressure, as shown in this graph of pumping speed in liters per minute as a function of pressure. After the rough pump reduces the chamber pressure to a few tens of millitorr, then we need to use a second high vacuum pump to reach a high enough vacuum for high yield thin film deposition. We will talk about high vacuum pumps in other videos. Now, let's go to Callie to demonstrate the mechanical pump.
I'm now in the sample prep lab outside of the clean room. We have put a marshmallow into the chamber because it will expand as the pressure in the chamber drops. This will enable us to see how the pressure is changing in the chamber as we pump the chamber with the mechanical pump. The chamber needs to be sealed so that air cannot get in when we pump it down and remove the air. Here is the O-ring gasket that seals the chamber. First, let's connect the input of the mechanical pump to a small vacuum chamber. Next, let's turn on the pump and proceed to evacuate the chamber. The mechanical pump is pretty noisy. As the chamber pressure drops, we can see the marshmallow expanding. Remember, the mechanical pump is what we call a rough pump. It will only evacuate the chamber to a few torr, or remove about 99.9% of the air. So in addition to the rough pump, we would need a high vacuum pump to achieve lower pressures. But the mechanical pump is sufficient for this demonstration. Okay, let's turn off the pump and we will now let air back into the chamber. As we go from vacuum to atmospheric pressure, the marshmallow collapses. Thanks for joining me today in the lab.